June 1941, Libyan Desert, 40 miles south of Tobruk. Lieutenant Colonel commanding a Crusader tank squadron watches another engine die. Black smoke, grinding metal, silence. That's the third tank today, and it's only noon. His chief mechanic opens the engine cowling and shows him the damage. The cylinder walls look like someone attacked them with sandpaper. Metal shavings glitter in the oil pan. It's the sand, sir. It's getting past the filters and grinding everything to powder. They've been in North Africa for 2 weeks. They've traveled barely a few dozen miles on proper operations. And now, a third of his squadron can't move. This isn't a story about enemy action. This is about something far more mundane and far more deadly: air filters, and how a simple engineering choice, one that American farmers had been using since the 1920s, would help determine who could fight in the desert and who couldn't. The problem nobody expected. When Britain sent armor to North Africa in 1940, many of its tanks were designed with European warfare in mind, rolling through French farmland, fighting in English rain. The engineers at the War Office had tested them thoroughly in European conditions. Almost nobody had stress tested them for what North African sand would do. Desert sand isn't like beach sand. It's microscopically fine. Particles measured between about 5 and 50 microns. For reference, a human hair is about 70 microns wide. This stuff can be finer than flour, and it hangs in the air for hours after vehicles pass through. Here's what happens when you drive a tank column across the desert. Each vehicle kicks up a massive dust cloud, tens of feet high, hundreds of feet wide. The tank behind you is driving through your cloud. The fifth tank in the column is essentially driving blind through a sandstorm of its own making, and that sand is trying desperately to get into every opening in your machine. An engine needs air, lots of it. A typical engine tank consumes thousands of cubic feet of air per minute at operating speed. That's a small house worth of air every minute being sucked through whatever filter stands between the outside and your cylinders. If that air carries sand, even trace amounts add up fast. A few grams of silica per cubic meter multiplied by that airflow means pounds of abrasive material trying to enter your engine every hour. What happens next is simple physics. Silica, sand, has a Mohs hardness of about 7.5. When you force a harder material between two softer surfaces that are sliding against each other, like pistons and cylinder walls, you get rapid wear. British tankers called it the grind. The engines would lose compression, burn oil, lose power, and finally seize. In some formations, engines were effectively worn out after only a few hundred miles of hard desert running, far sooner than crews had ever experienced in training. Why British filters failed. Many British tanks in 1941 used what were essentially dry element filters, metal canisters packed with treated fabric, felt, or similar media. Air passed through the fabric. Particles got trapped in the fibers. Clean air went to the engine. This worked reasonably well in England. Even in dusty conditions during training, it was often adequate. The problem was that North African sand wasn't in the test specifications when these filters were designed in the late 1930s. The fabric-type filters had 2 fatal flaws in severe desert conditions. First, they clogged very quickly. The ultra-fine sand particles would embed themselves deep in the fabric matrix. You couldn't shake them out. You couldn't easily blow them clean. The only reliable solution was replacement, and replacement elements were often in short supply. As the filter clogged, it restricted airflow. The engine lost power.
Desperate tank crews sometimes cut, removed, or bypassed parts of the filter element to restore airflow, and doomed their engines by letting poorly filtered air straight into the cylinders. Second, even when working properly, they struggled with the sheer particle load. In European conditions, you might change a filter after hundreds of miles. In North Africa, elements could need attention after a fraction of that to remain effective. A tank regiment with dozens of vehicles could require large numbers of spare elements for sustained operations, competing for cargo space with ammunition, fuel, and food. The statistics and unit reports were brutal. British armored units in mid-war North Africa complained that mechanical failures in some operations outnumbered combat losses by several times. Tanks that cost thousands of pounds were becoming immobile after a few weeks in theater. Captain Robert Crisp, 3rd Royal Tank Regiment, wrote in 1941 that he had gone through multiple tanks in a matter of weeks not from German guns, but from engine trouble. Fitters showed crews cylinders that looked like they had been filed down. Often there was little they could do in the field beyond swapping yet another worn-out vehicle. Meanwhile, German tanks were operating in the same desert with generally lower breakdown rates. Their Panzer IIIs and IVs were often able to cover longer distances with fewer engine failures. Why? Different filtration philosophy and earlier, more systematic preparation for dusty environments. The German advantage. German military vehicles widely used Badluftfilter, oil bath air filters. The principle wasn't uniquely German. It dated back to the 1920s, but German engineers had adopted and integrated it effectively across much of their vehicle fleet. British designers and engineers were not ignorant of oil bath concepts.
Technical literature and captured vehicles made the principle known, but procurement systems locked into existing contracts, designs, and production schedules did not always adapt quickly. Retooling production lines or significantly modifying engine compartments meant delays, and admitting that some existing assumptions had been inadequate. While committees argued and papers circulated, soldiers paid the price, not always from direct combat. A tank that breaks down during a retreat becomes a tomb if enemy forces arrive before recovery. A tank that can't move is a target, not a weapon. Here's the irony. Technology that would help solve the desert filtration crisis had been standard on much American farm equipment for years. In 1915, Frank Donaldson was selling engines to Midwestern farmers. He kept hearing the same complaint. Engines wore out too fast. Prairie dust from plowed fields was destroying them in a single season. Donaldson understood the problem. Existing filters, basically mesh screens, weren't stopping particles fine enough to damage cylinders. So in 1915, he founded Donaldson Company in St. Paul, Minnesota, to build better air filters. His solution was the oil bath filter. The design was elegant, a metal housing divided into two chambers. The bottom chamber holds a reservoir of engine oil. Regular oil, nothing special, a shallow bath. Incoming air enters through a tube that directs it downward towards the oil surface. Here's the key. The air has to make a sharp turn just above the oil. Heavy particles can't turn as quickly as air molecules. Inertia carries them down into the oil where they sink and stay trapped. The air continues upward through a gap above the oil surface. As it passes over the turbulent oil, tiny oil droplets are carried into the airstream. Dust particles stick to these oil droplets. Dust loves oil. The air, now carrying oil mists with trapped dust, moves into the upper chamber. In the upper chamber, a metal mash or similar packing provides surface area for the oil droplets to coalesce and grow heavy. As droplets combine and grow heavy, they fall back down into the reservoir, taking their captured dust with them. The cleaned air continues to the engine. The genius. It's self-maintaining. As dust accumulates in the oil, it settles to the bottom. You don't replace an element every short distance. You drain the dirty oil and add fresh oil. A few minutes of work using materials you already carry. By the early 1920s, oil bath filters had become common on American farm tractors, especially in dusty regions. Over the following decades, they spread into other off-road machinery and heavy vehicles. By the late 1930s, many American truck and equipment manufacturers used oil bath filtration in applications where dust was a serious threat. By the time U.S. military production ramped up, oil bath filters were simply what many American manufacturers considered best practice. It wasn't a special military revelation. It was the accumulated common sense of farmers, contractors, and truckers who had been fighting dust for decades. The M3 Stewart light tank, oil bath filter as standard equipment. The M3 Lee medium tank, similar. The later M4 Sherman, likewise equipped. American doctrine didn't make a big deal about it because to their engineers, if you were building equipment for harsh, dusty conditions, you used an oil bath filter. The American Arrival, November 1942, Operation Torch. American forces land in French North Africa. British commanders watched with interest as Shermans and Stewarts rolled off the ships. The Americans were green, inexperienced in desert warfare. British veterans expected they'd learn about the desert the hard way. But something unexpected happened. The American tanks kept running. After a week, American units were not reporting the same kind of catastrophic failure rates the British had endured earlier in the campaign. After 2 weeks, American formations had moved hundreds of miles with relatively modest breakdowns. After a month, British commanders wanted to know what exactly the Americans were doing differently. The answer was almost insulting in its simplicity. Different air filters, oil bath type. They say they're standard on all American vehicles. British liaison officers were skeptical. Yet American tanks were routinely covering several hundred miles between major overhauls, and some stayed in frontline service much longer than British crews had come to expect from their own early war desert machines. Senior British commanders, including Bernard Montgomery, pushed for direct comparisons between British and American tanks in desert conditions. During 1943, mixed columns ran over the same routes. Then, workshop crews stripped the engines. After 250 miles of severe dust, British engines, noticeable cylinder wear, scored pistons, heavily contaminated oil. American engines, much less wear, cleaner cylinder walls, more acceptable oil condition. The difference was filtration. The oil bath filters were capturing what British fabric-type systems often missed. Just as importantly, they could maintain performance with regular draining and refilling instead of progressively choking on their own captured dust. Internal British staff papers in early 1943 argued in plain language that continuing with inadequate filtration was costing tanks and lives, and urged rapid retrofitting with improved systems, often explicitly pointing to oil bath designs and American practice as examples to follow. But retrofitting thousands of tanks wasn't quick or simple. British tanks had engine compartments designed around existing filters. Oil bath units were often larger and heavier, requiring different mounting and piping. Some models adapted easily, others required substantial modification, and there was pride.
Admitting that commercial American technology developed in the 1920s and 1930s could outperform carefully specified British military equipment did not sit well with every official responsible for earlier decisions. While bureaucrats argued, soldiers acted. British tank crews scavenged oil bath filters from disabled vehicles and spare parts, including American ones, and jury-rigged them onto British tanks. Unit workshops fabricated brackets and adapter piping. It bent rules. It worked. Captain Douglas Brownlee, 2nd Royal Tank Regiment, recalled how his crew and fitters spent a day welding and improvising to fit a Yank filter to his Crusader. The engine ran cooler, pulled better, and the tank stayed in service longer than many unmodified sisters in the same unit. As official retrofit programs gathered momentum in mid-1943, British desert reliability improved markedly. The era in which mechanical breakdown threatened to halt operations as much as the enemy did was, if not over, at least clearly receding. Why it worked? The science matters because it explains why the change was so decisive. The most dangerous particles, the engine killers, are roughly 5 to 50 microns, invisible to the naked eye, angular with sharp edges like tiny glass shards, because that's essentially what they are, silicon dioxide, the same material as glass. When these particles get between a piston and cylinder wall, two surfaces sliding against each other thousands of times per minute, they act as microscopic cutting tools. Each particle cuts a tiny groove. Millions of particles, thousands of cycles, means measurable wear in hours and functional damage in days. Dry or fabric filters in desert service often failed through what engineers call depth loading. Particles penetrated the fabric and lodged within it. At first, this could improve apparent filtration because trapped particles caught more particles.
Eventually, though, the whole medium saturated, restricting airflow and driving crews to bypass or abuse the filter. Oil bath filters relied on different principles: inertial separation and wet scrubbing. The sharp turn in airflow above the oil exploited inertia. Heavier particles couldn't follow the airflow and fell into the oil. This dealt with larger and medium-sized particles. Smaller particles, the insidious ones, were captured by the oil mist. Dust sticks to oil. Simple physics, devastatingly effective. Crucially, as oil accumulated dust, it did not choke the air ream. Particles settled to the reservoir bottom. The surface oil layer stayed relatively clean between surfaces. Filtration efficiency remained high, even after processing huge volumes of dusty air, provided crews periodically drained and replenished the oil. In properly designed and maintained systems, oil bath filters could achieve very high capture efficiency for the size ranges that mattered most to engine wear, and they tended to maintain that performance more consistently in extreme dust than the early dry elements fitted to many British tanks. That difference, stable, high-efficiency filtration versus degrading bypass filtration, meant the difference between engines dying after a short desert tour and engines remaining serviceable across extended operations. Beyond North Africa, the oil bath filter story didn't end in the desert. Pacific theater, humid tropical conditions caused issues for some paper and fabric-based filters. Oil bath designs, by contrast, were less vulnerable to moisture and could keep working in heat and humidity. Italian campaign, agricultural regions during plowing and harvest created severe dust on roads and fields. British and Allied armor, now with improved filtration, inspired in part by desert experience, maintained operational readiness at levels that would have seemed impossible 2 years earlier. Northern Europe, even after D-Day, dust was a factor.
Unpaved Norman lanes, pulverized masonry in ruined towns, and summer traffic on country roads all created a brace of dust clouds capable of harming engines not properly protected. Soviet forces receiving American tanks through Lindleys often commented on their generally reliable automotive performance. Soviet engineers examined Western designs, including their filtration systems, and over time, some of those ideas influenced Soviet thinking about keeping dust out of engines in harsh climates. German forces, despite having adopted effective oil bath filters early, suffered from collapsing logistics and fuel shortages as the war dragged on. As maintenance schedules broke down and properly timed servicing became harder to guarantee, even good filtration systems sometimes could not deliver their full potential. A filter is only as good as the care it gets. The lesson? Oil bath filters didn't win World War II. No single technology wins wars, but they were one of hundreds of small advantages that collectively gave the Allies greater staying power in harsh environments. British tanks failed so often in 1941, not because British engineers were stupid, but because the procurement system had not fully tested their designs against North African realities. They had prepared for the war they expected, not the one they actually faced. American tanks succeeded in part because American industry had spent decades building machines for farmers on the Great Plains, contractors in the Southwest, and truckers on dusty backroads. Those customers demanded engines that survived dust. Manufacturers learned, iterated, and delivered. When war came, that civilian experience turned into a quiet military advantage. This pattern repeats throughout military history. Some of the best military technologies started as answers to mundane civilian problems: dust, mud, cold, corrosion, and were then adapted for war.
The worst are often those designed in peacetime by people who have never seen the true operating environment. Modern military vehicles use sophisticated multi-stage filtration, cyclonic pre-cleaners, high-efficiency elements, sensors that watch pressure and flow. But the core principle is the same one Frank Donaldson pursued over a century ago: remove the dust before it reaches the engine. British tanks in 1941 died early trying to breathe through filters that were never meant for a sandstorm. American tanks in 1942 and beyond ran longer because someone in Minnesota and many others like him had already learned the hard way that dust sticks to oil. Sometimes the difference between defeat and victory is not a new gun or thicker armor, but a better way to clean the air an engine breathes. That is the kind of knowledge wars quietly hinge.